Hi, welcome back to my YouTube channel. In this video, we're gonna see how we should solve this integral that looks terrifying and just confused mathematicians for a couple of decades or even centuries. I don't know. So how should we solve this integral? This integral does not have an antiderivative that can be represented in elementary functions. So we gotta use some tricks here. Suppose that I have a function x to the x. I can write it as e to the ln of x to the x. This is the same thing. So, x to the x is e to the x ln x. Now I can write this function as e to the x ln x dx. Let's remind ourselves of the Maclaurin expansion for e to the power of u, which is the sum from n equals 0 to infinity of u to the n over n factorial. If I write this in this form, I'm going to get x ln n to the power of n over n factorial dx, sum from n equals 0 to infinity. What I'm going to do here, for sake of convenience, I'm not going to write this summation notation here. I'm just going to write this index of n, and later you'll see index of k, and these two indices are summed over. If you want to get full marks on the exam, just write the whole thing here, write the whole summation. I'm not going to write it for sake of convenience and saving us some time. This is similar to Einstein notation, what I'm doing. If you've done tensor calculus, you know it, but yeah, you'll get the idea. What I'm going to do here, I'm going to say that so n factorial goes out because it's constant with respect to x. 1 over n factorial x to the n ln to the power of n of x dx. So what I can do here is I can say ln x equals t. Let me create more space down here for future work if we need it. So we can say ln x is t and e to the t equals x. If I differentiate both sides of this equation, I'm going to get dx equals e to the t dt. Now if I substitute what I got here, I'm going to be getting e to the tn, t to the n, e to the t dt. This is what I'm going to be left with, and it's going to be 1 over n factorial e to the t of n plus 1, because it's going to be e to the t n plus t. T can be factored out, and what I can do here is another substitution. I'm going to say y equals t times n plus 1, thus dy equals dt times n plus 1. Now my dt equals dy over n plus 1, and if I substitute all of this in my equation, in my integral, I'm going to get e to the y to the n, or over n plus 1 to the n dy over n plus 1. So now 1 over n factorial, this n plus 1 goes out, this n expands, and n plus 1 to the power of n also goes out, and we're left with e to the y to the n dy. Now 1 over n factorial, n plus 1, these two also get together. It's e to the y to the n dy. Now here I'm gonna do another substitution with Maclaurin series. I'm gonna introduce a new summed over index k, n plus 1, n plus 1. So if I write it in Maclaurin series again, it's going to be y to the k over k factorial of y to the n dy. This k is going to go here, 1 over n factorial k factorial n plus 1 y to the k y and to the n dy, 1 over n factorial k factorial n plus 1 y to the k plus n dy. So if I can integrate this function using power rule, it's going to yield a result of y to the k plus n plus 1 over k times n plus n, plus n plus 1 plus c, some constant of integration. Now if I substitute all these values that I did, substitute here, these two things right here, my final result is going to be a double sum from n equals 0 to infinity. You can do the substitution yourself. K equals 0 to infinity, but the final result is going to be n factorial k factorial n plus 1 to the power of n plus 1 times y to the, oh sorry, made a mistake here. So it's going to be n factorial k factorial n plus k plus 1 times n plus 1 to the power of k ln of k plus n plus 1 of x plus c, some constant of integration. So this is our final result of x to the x dx integral, which is indefinite integral, but for definite integral, as we're going to take another approach in other videos. So hope you enjoyed this video. If you did, please like and subscribe, and I'll see you next video.